This is a walkthrough of problem 2 on exam 1 in module 2, which is on page 49 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 2 is, a thin aluminum disc has a diameter of 30 centimeters. It is given a net charge of minus 0.4 nanocoulombs. Part A, how many extra electrons are on the disc? Part B, what is the electric field 2.5 millimeters above the center of the disc? Let's start with a good diagram. We can look at the disc from two different views, edge on and on the flat face. Part A asks for the number of extra electrons there are on the disc. We know the total charge is minus 0.4 nanocoulombs. We also know that the electronic charge, the charge on one electron, is 1.6 times 10 to the minus 19th coulombs. So we can set up a simple equation. The total charge is the number of electrons times the charge per electron. Solving for n, we get 2.5 billion. 2.5 times 10 to the 9th electrons will make a charge of 0.4 nanocoulombs. That's part A. Part B asks for the electric field 2.5 centimeters above the center of the disk. Right here, center of the disk, 2.5 centimeters above that point. Somewhere in there, right about there. So we have to consider a useful Gaussian surface. We want the field lines penetrating at a right angle or not at all. Matching the geometry of the problem and putting the Gaussian surface through the point where we want to measure the field, we can use a cylindrical pouch that snugly encloses the disk, like that, right around the disk. In the big view, it goes all around the edge like that. Now the disk is thin, which means that the area around is small compared to the big flat plate area. This curved area is small compared with pi r squared. I drew it a lot thicker in the diagram. So there's our diagram. Gauss's law is E dot A is 4 pi kq enclosed. This cylindrical surface has a flat top, a flat bottom, and a curved edge, same as the other cylinder in problem number 1, except a lot flatter. And this time, the field lines are going through the flat surfaces. Both the top and bottom have field lines going through them, like that. The field lines are coming in because the charge on the plate is negative. I should draw them all the way out here, but they start to curve away when you get near the edge. What about Q enclosed? Q enclosed is an important part of Gauss's law. What is Q enclosed? Well, we have the whole disk. And the charge on the disk is minus 0.4 nanocoulombs, so Q enclosed must be minus 0.4 nanocoulombs. That was straightforward. So that's the right-hand side. Now we got to do E dot A. We're going to ignore the curved edge because it's so small. The area of the top surface is pi r squared. Same as the bottom surface. Field lines are going through the top and the bottom surface. So we E dot A, the field lines are going in, the vector's going out. It gives you a negative sign when you dot E into A. I'm not worried about the negative sign. I know which way the field's going. The field's going towards the disk. I'm just looking for the magnitude. So E dot A is 4 pi kq enclosed. E dot A is 2 pi r squared times E. And there's the charge enclosed. So we can solve for E. And we remembered that the diameter was 30 centimeters, and this is the radius. So we put in 15 centimeters for the radius. Converted the charge to nanocoulombs. Punch in the numbers, we get 320 nanocoulombs. And we know, because the charge is negative, that it's downward. So the answer to part B, because it asks for the field 2.5 millimeters above the surface, and the field is downward toward the plate. That's problem 2, exam 1, module 2.